Yes.
Okay.
How about present?
Yeah, is that okay? Got a little bit of an echo on my side, but I think it's okay as long as it's not bothering you guys. Thank you, Yao, for the introduction. And I'm sorry I can't be there. I've heard a lot of how beautiful the campus is down there. So maybe one day I'll be able to make a visit. So yeah, and thank you everybody for coming to the talk. Today I'll be exploring solid Earth dynamics across what's known as the Mid Pleistocene Transition. And so this work is very much in progress. I'm happy to welcome feedback, good and bad. And, I do have a pretty thick skin, so, bring it on. And so what do I mean about solid Earth dynamics? And I'm actually talking about a really specific process called glacial isostatic adjustment. So under the load of an ice sheet, the lithosphere, so here this tectonic plate and the mantle beneath will deform and warp downwards, causing subsidence of the crust. The reduction of an ice sheet will drive the return flow, and so the crust will rebound. And so both responses can involve elastic and or viscous deformation of the solid Earth. And so we see this happening today in response to the last glacial maximum, so the peak of the last ice age, which happened around 21,000 years ago. Here, what I'm showing you, if you can see my mouse, I hope you can, are GPS stations scattered all over Scandinavia, showing today's uplift around the Scandinavian region due to an ice sheet that completely vanished about 7,000 years ago. And so you see these rates reach around 1 centimeter a year. And again, in North America, the now extinct Laurentide ice sheet still shows its effects today. So this ice sheet expanded right down to Long Island. And so here are GPS stations showing the uplift across North America due to the melting of that ice sheet, again, completely vanishing around 7,000 years ago. And as you see, we've got subsidence basically south of the Canadian-American border. And as you can see, Canada's always moving to higher places. What can I say? Okay, so this delay, or the fact that deformation is still ongoing, is because of the sluggish viscous flow of the mantle. And we'll learn that this ends up being very important. And I forgot to say at the start, but please do interrupt if there's any clarifications you need or any questions that come up. And so the Pleistocene is really defined by the appearance of Northern Hemisphere ice some 2.5 million years ago. And by Northern Hemisphere ice, what I mean is the Laurentide ice sheet, so this one here, the Fennoscandian ice sheet, and still present today, the Greenland ice sheet. And this is what ice cover looked like during the last glacial maximum, the peak of that last ice age. But if we go farther back in time, we can begin to see patterns in the history of Pleistocene ice. So one of the most powerful proxies that we use to infer ice volume are oxygen isotopes found in marine sediment cores, measured in benthic foraminifera, so these tiny little shells that hang around the ocean floor. And this is perhaps the most famous figure depicting a stack of many of these cores going back several million years by Lorraine Lasicki and Mo Ramo. And so here, low delta 18O basically indicates warmer times or times with less ice volume, and higher values indicate times of large ice sheets. And so here on the y-axis, they flip it oftentimes so that higher, upwards or lower values of oxygen isotopes means warmer times, right? And so let's look at some of these notable features. So here we are today, and it goes back to kind of 3.6 million years ago here. Here we are today. 21,000 years ago, we have the last glacial maximum. And from then to today, we've got the deglaciation happening from about 21 to 7,000 years ago. And this deglaciation wasn't steady. There were lots of really kind of high melt events like meltwater pulse 1A around 14,000 years ago. And so, as I said, it wasn't steady. There were pulses of different types of events. The lead up to the last glacial maximum from the last interglacial around 120,000 years ago was much steadier, taking up around 100,000 years. And so what you get is slower growth of global ice volume, but definitely this growth wasn't steady also. But these zigzags are essentially signs of Earth's climate flipping between ice ages and interglacials. And so ice ages in the Northern Hemisphere really nucleated around 2.5 million years ago, right at the start of this red box. And what you see over that 2.5 million years is a steady increase in the amplitude of ice ages from then till now. I'm not sure I need to spend a lot of time convincing folks here too much of the importance of studying Earth's climate. And I guess this phrase here I've highlighted is somewhat cliched, but the distinction I'd like to emphasize here, especially in this geophysics department, is the importance of considering the Earth system as a whole. And just because of my own bias, here are some examples of where solid Earth dynamics becomes a major player in these climatological issues. So first is the Pliocene. So this is a period around 3 to 5 million years ago. Paleo shorelines record sea level at this time being anywhere between 15 to 60 meters higher than today. And so now that's pretty problematic because the Pliocene is special since its tectonic and atmospheric CO2 conditions are really similar today. Its CO2 conditions are perhaps a little bit more elevated, so it's often treated as an analog for where we might be heading. And while I'd like my hometown of Manchester to be a beach town, I'm pretty sure these paleo shorelines would put San Diego and Berkeley under sea level. So a key element to understanding and interpreting those paleo shorelines, that kind of puts sea level tens of meters higher than today, is actually really understanding what the solid Earth, how that's deforming underneath, right? Because we define sea level as two surfaces, the sea surface, but also importantly, the crust underneath. And I actually had an opportunity to see part of this famous Pliocene shoreline when I was in the Southeast, and it's called the Orangeburg Scarp. And so as someone who really never gets to do any field work, I was like pretty excited about this opportunity. And so here is this beautiful geological site. There it is. If you can't see, there's a tiny kink in the road, and that is this paleo shoreline. There are much better exposures of it, but this was the part I got to see while we were driving. So it was a little bit disappointing. Another example involves how during ice ages, we get basically near synchronous ice change at both hemispheres, even though insolation forcing would be antiphased. And so in a really neat study, Gomez and her colleagues showed that solid Earth dynamics basically can drive a sea level forcing from one pole to the other, such that you essentially sink ice growth at both poles. And so in this talk, we'll talk about another example. And so these ice ages that I've described are often connected to Milankovitch cycles, which I'll discuss in a few moments. But, as an enthusiast of the history of science, I thought I'd take this time to kind of put Milankovitch into a little bit of context, since we actually have just passed his 200th year anniversary of when he published his really early work on these ice ages. And so what Milankovitch did is that he proposed that orbital changes result in changes in Earth's insolation that could control climate. And he actually formulated much of these ideas as a prisoner of war in 1914. And in our own, personal situations during shelter in place, I had to reflect, as a prisoner of my own one-bedroom Oakland apartment. And trust me, that is British sarcasm. A prison is a very generous word for my apartment. But I had to think, during lockdown, what did I achieve? And honestly, it mainly boils down to watching far too much soccer, and certainly not being anywhere near as productive as Milankovitch. And so after the war, there's this really lovely quote from his journal. And so I'll read it to you here. After a comfortable 3-day cruise down the River Danube, I arrived to Belgrade on March 15th, 1919, thus completing my exciting 5-year wedding trip. He had just gotten married before he had been arrested, but it's really nice to see that kind of dark Eastern European humor didn't leave him, even after being a prisoner of war for so many years. Okay, But upon leaving in 1920, he then published his seminal work on these ice ages. And I'm not even going to attempt to pronounce the French here, but if you ever want to see, that's the citation. The most important thing about this, to me at least, is really that all his ideas predate core data. And he continued developing these ideas through the early 20s, and these are documented in really well-preserved letters to another prominent Serbian scientist. And they basically describe conversations that Milankovitch had with, very famous geologists of past, like Wegener and Köppen. And there are some really nice moments if you read the translation of what I like to call gentleman trash talk, where, Milankovitch dismisses pretty brutally, but very politely, Sales's ideas of ice ages being connected to volcanism in favor of Wegener's ideas, for example. So if you ever get a chance, they're all online. But the letters also detail difficulties of Milankovitch publishing these ideas, since there was actually very little evidence for any of his ideas. And so ultimately, I wanted to talk about this to highlight just different means of the scientific process. And, as a theoretician myself, it is really easy to propose ideas, but it's harder to show that they're true. Nevertheless, attempts were made to make use of Milankovitch's ideas. So this slide is actually a culmination of several hours of one of those days where you just procrastinate. This was a kind of 6-hour rabbit hole delve into early 20th century lust studies. Lusses are basically windswept deposits. So amongst the 1920s Germanic and Baltic lust stratigraphy community, much potential was actually seen in Milankovitch's ideas. And so actually the earliest attempts of chronostratigraphy, so this is a practice that underpins paleoclimate today, involved two lust paleosol Hungarian geologists, and they tried to calibrate what they called the environmental phases using Milankovitch's ice age calendar. But finally, perhaps 15 years after Milankovitch's death, the classic Hayes et al. Paper came out showing that strong connection between the ice age frequency content from core data and Earth's orbital cycles. And so now Milankovitch's theory really lays the framework for paleoclimate, and in particular, trying to understand the climate system feedbacks in response to these orbital changes. And so what are these orbital changes? And so from low to high frequencies, these are first the eccentricity. And so the eccentricity varies roughly around every 100,000 years. And if you can see my hands, basically that's how eccentric the orbit varies from. And so our Earth's orbit is near circular. So these variations are very slight. Next is the obliquity. So that is the tilt of our axis that controls the strength of the seasons. And that varies around every 40,000 years. And so on top of that, we've got the precession. And this we've got this thing going on that's a bit like this. Sorry about my very small Zoom screen. You have to kind of imagine this basically. But that varies every 21,000 years. And so within the context of the oxygen isotope record and Milankovitch cycles, there are several mysteries or conundrums. And so the first is how orbital cycles can drive ice ages. So these orbital variations are extremely slight, and the resulting changes in Earth's insolation are equally slight. So incredible feedbacks within Earth's climate system must be at play to drive extremely large climatic variations like ice age cycles. And what's perhaps even more puzzling is that if you look at the frequency content of the ice volume in, say, the last million years, these are dominated by the eccentricity cycle. So here I'm showing you the last 500,000 years of the oxygen isotope record here. And on the right is the power spectrum. And so there's the eccentricity, the obliquity, the precession periods. And what you see again is dominated in the eccentricity cycle. And yet, if we look at changes in insolation, and we always use summer insolation in Northern Hemisphere, there is basically no power at the eccentricity period. So what we have here is insolation in time series, and this is the associated power spectrum with that, and there's very little power at the eccentricity period. And so that's conundrum one. While dramatic ice ages seem to be paced at the eccentricity period, the Milankovitch cycle show the least power at this periodicity. And so the second conundrum is that going further back into the early Pleistocene, this was actually dominated by the 40,000 year obliquity cycle. So this is around this period shown in red, until mysteriously switching to the 100,000 year cycle that we've had for the last million years. So nothing about Milankovich's cycles, the forcing has changed, and yet Earth's response to this has. And so now this transition is what we call the Mid Pleistocene Transition. This was also accompanied by a general cooling of the climate so that the ice age amplitudes increased to today. And so this figure shows a little bit more clearly. Here we have the contribution to the ice age signal from each periodicity over time. And so this is going back 5 million years. And so the precession cycle in this dashed line remains small throughout. The obliquity cycle remains somewhat strong through the Pleistocene with some variation. And so that's the solid black line. But the real change is that the contribution from the eccentricity cycle begins to dominate over the last million years. And so there have been some proposed mechanisms, but no real convergence. Peter Hoybers argues that the shift actually represents perhaps a beating between the 20 and the 40,000 year precession and obliquity cycles, rather than a fundamental switch to responding to the eccentricity cycle. Changes in ocean sea ice dynamics and switches from terrestrial to marine-based ice sheet margins have also been proposed to drive the switch. Most recently, the regolith removal hypothesis has been revived. This is basically to do with ice sheets gouging out the underlying regolith so that the basal surface conditions of the ice sheet changes over time. And so even if the forcing is identical, that bottom boundary layer of the ice sheet is evolving. And so I actually really like this idea. I wish it were mine. You know, when you read papers that you, that's a good idea. Having said that, though, there is some geological evidence to believe that the actual erosion history might not have been as gradual as these modeling studies require. So it's still up in the air. The final conundrum that I'll address is the asymmetry in the rates of ice growth and decline within a single cycle. And so the ice ages in the last million years are characterized by that slow growth and rapid decline, giving them that kind of classic sawtooth pattern. And I mentioned that earlier. This wasn't always the case throughout the Pleistocene. So over the Pleistocene, the ice age cycles have become increasingly asymmetric, where in the early Pleistocene, growth and decline were roughly symmetric. And this is kind of shown in this figure where these are rates of ice change, where deglaciation in the black and glaciation in the dashed line start together in the early Pleistocene, but start to diverge, where rates of deglaciation exceed rates of glaciation as we move to present day. And so those are the three conundrums that I'm going to discuss today. And so just to summarize them, what we have is, firstly, how these tiny changes in insolation can drive dramatic changes in climate. Second, what caused the transition from obliquity to eccentricity dominated ice age cycles, or what drove the mid-Pleistocene transition? And finally, what is causing the asymmetry in growth and decline of ice to increase over the Pleistocene? And what I'd really like to discuss today is the role of the solid Earth in all of these kinds of processes. And so first, a brief primer in very simple ice physics, and what I describe here is as sophisticated as it gets for me. But what you can do is define an equilibrium line or surface, shown schematically here, this black line. If you are above this equilibrium line, precipitation will fall as snow and you will add to the ice sheet. Below this, you are in the ablation regime where you lose ice. And so the growth of ice can be determined by changing the position of the equilibrium line. And so if we pretend that this schematic depicts the North Pole, where we have the Arctic Ocean here, the equilibrium line shifts between summer and winter. When the summer, it's such that no ice sheet is able to form. The other way to determine the presence of ice is rather than moving the equilibrium line, you can move relative to it. So the presence of ice can be changed if you increase or decrease your altitude. Now, what the solid Earth does, as I mentioned, under the load of an ice sheet, the crust subsides. Upon unloading, the crust rebounds. And so you're basically moving the ice sheet because of this deformation relative to the equilibrium line. Now, the time scale of this process matters. Remember, I began the talk showing present-day GPS rates of uplift across Scandinavia and North America due to ice sheets that vanished 7,000 years ago. Viscous stresses in the mantle is the cause of this delay. And so what geophysicists that model glacial isostatic adjustment is, how we do this is that we think of the Earth as a viscoelastic solid, consisting usually of an elastic spring and a viscous dashpot in series. And so eta here will be the symbol for viscosity throughout the talk. And viscosity is simply a measure of a fluid's resistance to flow. So high viscosity fluids will flow slowly like the mantle, which really creeps. And so you can imagine applying stress to this contraption. I'm just imagine this spring and dashpot in between my hands right now. And depending how fast or slow you apply this stress, the spring or the dashpot will deform at different degrees. And so to model GIA, or glacial isostatic adjustment, we really have to know these parameters, the spring constant K and the viscosity, and how they vary within the mantle. Now, the time scale of relaxation really depends on the ratio of these two given their dimensions. And so since the elastic constant doesn't vary nearly as much with depth as the viscosity, it's really the viscosity that dominates changes in relaxation time scale. And so more specifically, can GIA, or glacial isostatic adjustment, play a role in these conundrums? Okay, so the first conundrum, why do we have ice ages paced at the 100,000 year cycle when eccentricity virtually has no effect on insolation? So in a really high profile paper, Abiuchi and her colleagues coupled a climate and ice sheet model together to explore this, and we're able to produce the 100,000 year cycles. Now I've pulled a line from that paper and I'll just read it directly. This result supports the idea that the crucial mechanism for the 100,000 year cycles is the delayed glacial isostatic rebound. And so basically in their coupled ice sheet climate models, if they remove the delay of crustal rebound, what they'd actually have is a protracted ice age with permanent ice cover. So the reason behind this is because as the ice sheet grows, the crust subsides. And upon rapid melts, viscous stresses that delay that rebound keep the ice sheet low relative to that equilibrium line. And so at these low, warmer altitudes, melting is enhanced such that you don't get a permanent ice sheet. Now, they actually modeled the bedrock elevation or crustal subsidence back with this differential equation. And they chose, importantly, this timescale tau of around 5,000 years, which actually is not unreasonable when we think about mantle properties. But just to give you a better idea schematically, this is the process, right? So we have that ice equilibrium line and our ice sheet above it. And this ice sheet is growing. Under the weight of that ice sheet, we drive mantle flow and it causes the crust to subside. This continues right up until the maximum height is reached. And as you move into a melt phase, the melting is more rapid than the flow of the mantle. And so viscous stresses within the mantle delay that rebound. And ice is kept at low altitudes where it's warmer, And so this melting is enhanced. And so you kind of escape the permanent ice sheet scenario. And so today, North America, we're in this current phase where we're still uplifting even without the Laurentide ice sheet. And I just want to note that this idea isn't new. Abiuchi really brought in all the systems and looked at this in a really state-of-the-art manner. The idea of bedrock elevation has been around since the classic glaciologists from the 70s and 80s, including Olemans. And here, this is a study from Pollard, which basically showed very similar results to Abiuchi, though with a much simpler ice sheet model. And this was his differential equation that describes crustal uplift, where this parameter nu is related to 1 over the viscosity. Now, I hope that those studies have somewhat convinced you of the important role of crustal subsidence and uplift in the 100,000-year late Pleistocene ice age cycles. What I'd like to explore is how the same process might drive the Mid Pleistocene transition. So conundrum number 2. So now returning to Abiuchi's simple differential equation, looking at this from a geophysicist's perspective, a single relaxation time just does not sit well with me. The only way this can be true is if the mantle is isoviscous or has a single viscosity. So the results I'm going to share with you today are based on 2 really simple, well-established ideas in geophysics. Firstly, larger surface loads, in our case, ice sheets, sense deeper parts of the mantle, or they'll induce deformation that penetrates deeper into the mantle. And the mantle's viscosity eta increases with depth. The consequence of these 2 facts is that the value of the relaxation time here now, tau r, will change with different ice sheet sizes. And so the first point, if we take the simplest geometry and infinite half space, say, an ice sheet of length scale lambda will induce deformation that scales with lambda. And this is true just thinking about the dimensions of this problem. The independent length scale here is the width of the ice sheet. And so this larger ice sheet will be sensitive to deeper regions within the mantle. That second point is that the mantle's viscosity increases with depth. And so now the mantle viscosity world was a treacherous world. I've heard stories of vitriolic AGU sessions in the 90s, but I wasn't around then. So, I mean, I was around, I just wasn't aware of mantle viscosity then. But as of 2004, this is a selection of some of the mantle viscosity profiles. So here is the surface right down to the core mantle boundary on the y-axis, and viscosity on the horizontal axis spanning 10 to the 18 Pascal seconds to 10 to the 24 Pascal seconds. And so we're looking at order of magnitude changes. But as of 2004, they really group into 2 camps, one shown in the oranges, where several geophysicists see the mantle as essentially isoviscous, and the other in greens, where the viscosity increases by several orders of magnitude with depth. So more recently, this dichotomy still somewhat lingers, but we did a study early in 2016 where we basically used the same data set that the studies that proposed an isoviscous mantle used. But what we did was to take a specific datum, this was kind of the long wavelength geoid, and applied up to the date corrections of modern anthropogenic ice melt, which actually contaminate that signal. And if you do that, you actually get a profile that increases substantially with depth, reconciling the 2 differing views of mantle viscosity. But here are other independent inferences of mantle viscosity. The one on the left shows experimental results on the upper mantle rocks that would predict viscosity increases with depth, albeit with significant extrapolation. The one on the right shows a combined seismic and geodetic data inversion that actually resulted in viscosity increasing by 2 to 3 orders of magnitude with depth. And so given the idea that the field is somewhat converged on the fact that viscosity does increase with depth, how does the relaxation timescale or the rebound timescale change given that? So we're going to do some really simple calculations to explore this. First, I'm going to take a smooth version of the previous viscosity profile, this black line. It's smooth basically by dictated by the resolving power of the data used to infer it. What we'll do is we'll test that profile here shown in blue, where we have from the surface to the core mantle boundary, viscosity on the y-axis increasing. We'll test this against an isoviscous model, this orange model. Now, what we'll do is grow several ice sheets of different maximum widths HW. Again, keeping the geometry simple, we'll just imagine this Earth here. I'm going to grow and shrink ice sheets that are longitudinally symmetric across the equator. So just imagine across the equator, we're kind of growing ice sheets and shrinking them. And just to show you what this looks like, here's a quick clip where X here, 0 is the equator. Yep, and here we go. This is our ice sheet growing. And then we melt it. And what we're going to do is measure the relaxation time. So that rebound time, the time scale of that rebound, once it's in free decay, and fit basically an exponential decay to get that time scale. So what we're going to get for each growth and decline of a certain width, HW, we're going to get an associated tau R. And so this is the result of that. So as expected, if the time scale is dictated by the viscosity or eta over the spring constant K, if viscosity increases with depth, then larger ice sheets will have longer relaxation timescales. And here that's this trend. So larger ice sheets on the x-axis and the timescale on the y, and we see that increase, right? The isoviscous relaxation times are basically invariant. And so just to emphasize that point, here I'm showing you a sensitivity kernel of that relaxation time to different regions within the mantle as a function of a given ice sheet's width. So on the x-axis, this is an indication of that sensitivity to mantle viscosity. On the y-axis, this is the depth throughout the mantle. And so darker colors are the sensitivity kernels for wider ice sheets, and the lighter colors are those for the smaller ice sheets. And as you can see, those lighter lines, so the smaller ice sheets, peak in the shallow mantle, whereas larger ice sheets have significant sensitivity at depth. Okay, so now we've established that larger ice sheets have longer relaxation times. How does that actually fit in with the transition? So I'm not a climate scientist and I don't know how to run coupled ice sheet climate models. So I turned to a classic paper by Marsh and Saltzman. And so these two developed a pretty parameterized climate model that's supposed to have all the features of the feedbacks between the cryosphere, the atmosphere, and the ocean. And they postulated that the early and late Pleistocene represent two distinct solutions in their system of coupled equations. And upon forcing the equation with a Milankovitch insolation and changing various control parameters arbitrarily, they showed that you could flip between the two different solutions. And so it's actually intriguing. In their closing paragraph, they note, we assume that a slow progressive change in model parameters associated with an as yet unidentified change in the tectonically forced equilibrium system could be the cause of the mid-Pleistocene transition. And so we're going to use their system of equations as a framework to test our idea and ask if changing tau R could be this unidentified change in tectonics. And so here are those coupled equations. This is actually in a later paper that focused on bedrock subsidence. And these basically describe perturbations in the rate of ice mass change and bedrock subsidence B. And so just to give you some intuition, I'll walk through these terms briefly. So this first term basically represents some mean climate state. The second term captures kind of internal ice deformation dynamics. Now, this is quite an important one. The C is a function that accounts for ice carving. So if bedrock subsides to a point where actually the crust is beneath sea level, you get inundation of ocean water, especially the Arctic Ocean. And that inundation of water carves the ice sheet. And finally, we have the forcing, the Milankovitch insolation. And so this is for the bedrock substance. This is basically a conversion of ice mass I, and this is where they're coupled to ice height, right? And so the substance depends on how tall the ice sheet is. And finally, we have that bedrock relaxation timescale, tau r here. And so as I changes, we adjust tau r accordingly. Remember, we have this ice width here, which we can convert to ice mass. And how that changes through our simulations, we'll choose the associated tau r. Okay. So a key ingredient is that we need a secular change to drive larger ice sheets. And this is provided by the fact that climate was cooling throughout the Pleistocene. And so to mimic this for our ice sheets, we're going to take a secular trend through the oxygen isotope time series. And we'll use actual values from Saltzman's and Marsh's papers to match this decline to changing background states of growth rate. And so as the ice masses get bigger, what we're going to do, as I said, is adjust tau r as this simulation evolves. So here are our results. Okay, so just to orientate you, on top is are the oxygen isotopes. We're not going to model this. This is here just for comparison. Then we have the Milankovitch forcing. So that's the forcing of our equation. We're going to track the relaxation time, which depends again on the ice mass. And then we're going to show you the ice mass itself. Okay. So we're going to start with the isoviscous mantle. I'm going to press play. And so if you suffer from epilepsy, please just stare at this line because the others are a little bit jittery. As you can see, since we've imposed our secular trend in ice mass change, the general amplitude of the ice, of each ice age grows, but we don't really see a change in periodicity, right? And again, that relaxation time is basically invariant across this whole time period. So what happens if we have a mantle that is not isoviscous? And so here are the results from the mantle in which the viscosity increases with depth, right? As you can see, as we reach a certain relaxation timescale, we switch from one state of the system to another. Here it is. So, sorry, I don't know if you can see the play bar, but what you can see is a simple change in relaxation time is sufficient for this switch to occur within the Marsh and Saltzman's kind of framework. And so just to note, we tried many different sort of secular histories, and the switch always happened. It was really just the timing of the switch that changed depending on the history we chose. But if we now look at the power spectra of all these records in the early Pleistocene, what we see is that, again, this is eccentricity, obliquity, and precession. What we see is that the obliquity cycle dominates for all three. So the gray line is Milankovitch. So the forcing, the red line is oxygen. So kind of think about that as the data we're trying to fit. But both ice histories, so the isoviscous and the non-isoviscous one, peak at the obliquity cycle in the early Pleistocene. What happens if we switch to the late Pleistocene is that peak remains the same for the isoviscous mantle, but the oxygen isotopes move to the eccentricity cycle, as does the simulation with the non-isoviscous mantle. And so finally, the last conundrum, where I'll make much more of a speculation if that already wasn't. So I'm going to suggest that increasing tau r also has the potential for increasing the asymmetry in growth and decline patterns of ice ages. And so I said earlier that since larger ice sheets are associated with longer relaxation timescales, that causes the enhanced melting due to the delayed rebound. So you're going to speed up melting because you're keeping the ice at lower altitudes, right? And so that was key to those early studies reproducing the 100,000-year sawtooth cycles. I didn't expand on this earlier, but when you subside, you also induce even more enhanced rates from calving, which I touched upon. So specifically for the Northern Hemisphere ice sheets, especially on the North American continent, what you're going to do is cause inundating Arctic Ocean waters to enhance that melt further. So you really do get that kind of sawtooth pattern. In contrast to this, smaller ice sheets, so if we look on this side of the diagram, have shorter relaxation times. And so they rebound much faster. And so in this scenario, melting could be just as steady as growth. Moreover, I kind of simplified the discussion earlier on. Here was the previous schematic I showed you. In reality, the situation is more like this. We have a really thick tectonic plate, especially under the Canadian Shield, which basically behaves elastically. So very small ice sheets might not even have much delay at all. And so to summarize those three conundrums and the role of GIA in them, I explained how previous authors found that glacial isostatic adjustment was crucial in reproducing those 100,000-year ice age cycles. But what I've suggested is that the timescale of this adjustment varies with the width of the ice load, and that the trigger from the switch to 40 to 100,000 years and the increase in asymmetry of those ice age cycles could be due to a change in that relaxation timescale. And so to go back full circle, is there any evidence of this, or must we wait like Milankovitch had to? Hopefully not, because he had to wait until after his death. Okay, so there's actually a really nice data set I've been looking at for a long time that I didn't really make the connection until recently, but as modelers or theoreticians in the geophysics geophysics departments, it's really nice if we can fit data, and we typically fit geodetic or seismic data, but we rarely get to kind of look at geological data. So there's this classic data set. Here are regions of Scandinavia where the landscape has really been shaped by the past ice sheets. So here's an esker in Angermanland, for example. This is kind of southern-ish Sweden. But more specifically, there's this beautiful stretch of strand lines that mark paleo shorelines as the Fennoscandian ice sheet retreated. So if you can make them out here, I'm not sure you can, depending on your projector. But a classic study by McConnell explored this really rich data set compiled by Saramo in the 50s. And so this data set really was the culmination of years of efforts by Baltic region geologists. But here's that paper, and I think you're getting an idea that I really like reading old papers, but one of the figures here shows the transect. I don't know if you can see my mouse, but this is the transect of the strand lines that McConnell used in this paper. And in this figure, the heights of these strand lines are placed next to their age, right? And so this line here is the Angerman esker that you saw before. And what you do is basically track the elevation history of these strand lines. And what McConnell did was that he took a spectral approach that related the characteristic length scale of ice loads with the time scale of these elevation histories. And so what I'm showing you is actually a more recent study where Wysokowski did the same calculations with revised dates on those strand lines. But ultimately, what you see is an increase, with increasing spherical harmonic degree, or basically shorter wavelengths, the relaxation time scale decreases. And that is exactly what we would like to see. And so hopefully I've convinced you that at least the variation of relaxation timescale is worth a closer look at within the context of Pleistocene ice ages. And so the next steps is to really put this to the test. We've only used simple ice sheet geometries with a very simple secular trend. And we embedded this in Marsh and Verbitsky's coupled equations, mainly just to demonstrate the feasibility of this idea. Conversely, coupled ice climate models that have the machinery to consider the climate system more completely used a very simplified view of crustal rebound. And I put it here, the solid Earth is so much more than a single Greek letter. And so I do think that perhaps we need to incorporate a more comprehensive view of Earth's rebound dynamics into these kind of ice climate models in order to account for all the potential feedbacks that control our long-term climate state. Thank you all for listening. I'll just list a few acknowledgements here. I've had some very great discussions with glaciologists like Kurt Coffey and Greg Balko, my old advisor who basically, when I pitched this idea to him, encouraged me to pursue it, and also UC Berkeley. And I'll leave the summary here and take any questions. Thank you.
Thank you so much for the fascinating talk, Harriet. So let's try first to take questions from the audience in the conference room. And for people on Zoom, please just like unmute yourself or type your question in the chat. Go ahead.
I was surprised that you didn't mention the asthenosphere. Could you explain why you didn't mention that? And also, I was taught that the asthenosphere has so much lower a viscosity that it was the primary locus of, sublithospheric flow, and it was more lateral flow in the sense the asthenosphere has such a low viscosity, it's kind of flowing sideways to get out of the way to allow for the ice sheet to make a big hole. Is that wrong?
No, you're completely right. Yeah. So sorry, who's asking the question?
I'm just curious why you did not mention the.
Oh, no, I got the question. I was just asking who's asking the question, so I can at least put
Jeff Stebringhouse.
Oh, hi. Okay, great. Sorry. Yeah, Jeff, no, that's completely right. So actually what you find, and that's a kind of detail I should certainly touch upon now. So when the ice sheets that exist in the Northern Hemisphere, especially the Laurentide, but also the Fennoscandian, it turns out, just given how large they got, and you can think about it in terms of that kind of sensitivity analysis. They actually have very little sensitivity to that shallow mantle just because they're so large. They span about 3,000 kilometers. And so you sort of scale that with the amount of mantle that they see. So the asthenosphere seems really thin. But I think you've got a great point because, those smaller ice sheets are really going to, be quite sensitive to kind of if there was a low viscosity zone. I haven't put it here, but for sure, I think that might even enhance the effect. If you've got a low viscosity sort of zone right beneath the lithosphere, those smaller ice sheets will be very sensitive to that and would probably have much shorter decay times with that there. So yeah, no, thank you. Sorry, yeah, I should probably expand on that next time.
Thank you.
Yeah, thank you. More questions?
So Harriet, maybe a naive question. I just wonder if topography gonna have influence on the elastic rebounding and the viscosity measurement.
So topography on the viscosity measurements, was that right? Sorry, it was a little bit broken.
Yeah, because I'm assuming that current modeling have not considered topography inside, right? The topography means the like the mountains and the topography we have seen currently. I guess it's not strongly influencing the result, right? But I'm not sure.
Right. That would be, I mean, topography is actually in terms of ice sheets, it's very important. So actually where we think, the Laurentide ice sheet nucleated is in the highest points of the of Canada, right? Basically around Around Baffin Island, we think that's where it nucleated because of the altitude. In terms of aspects of topography that are very important, once you get the subsidence and anything marine based, you suddenly kind of make the ice sheet very vulnerable. I'm definitely not an expert on this, so but for example, the Western Antarctic ice sheet, that's a marine based ice sheet because the continent itself is underneath sea level. So that certainly makes in terms of the context of glacial isostatic adjustment, I think that seems to be the kind of bigger control. But for sure, this is very simplistic, that there are no ice dynamics in the stuff I've sort of explored. My guess is that topography plays a very big role in that. But I think you mentioned in terms of viscosity of the mantle, or maybe I misheard.
Yeah, I think well, I think it's the right idea. I was just trying to understand the influence of potential topography on the measurement of the mantle viscosity using the glacial rebound, and I think you are answering the right question.
Right. Okay. Yeah. Yeah. So the topography doesn't fall into it too much in terms of inferring viscosity of the mantle. Thank you.
Thank you.
Can I ask a question? It's good to see you again, Harriet. I wanted to come along to this talk again because I've been thinking about this quite a lot. So I actually have two things that I wanted to ask, if that's all right. So first one is you're using oxygen isotopes as your observation here, but I was wondering if you could also talk about the delta C13 isotopes as well, because we see similar sort of period power transitions in the delta C13 record, but I don't know how that ties in with this sort of solid Earth glaciation story.
Yeah, that's a good question. I'm not gonna be able to answer too much on that, mainly because I don't really know. I know that the C13 record is sort of, a lot of the context of this the ice ages has been whether, is there a lag or which leads, right? Is it changes in CO2 in the atmosphere versus changes in ice volume? So I'm not sure. Maybe if someone who is an expert on these isotope proxies could chime in, but I would say that a really good data set that would be very helpful here, but is kind of really scarce, is actually continental based data. The bad thing about ice sheets is that they basically erode everything they kind of grow into, and so there's very little in the way of just actually trying to track the volume of the ice sheet, because obviously the oxygen isotopes are somewhat, they conflate temperature effects also. But the C13, maybe I'll read up on that. Well,
okay.
Give him homework.
Yeah. I'll send you a paper if you like.
Okay. Yeah, I'd love
and there was another thing that I wanted to talk about. It's sort of like, putting this work into the broader context of other period changes in the Cenozoic, because I was sort of reading back up on it, and there are actually some changes sometimes in the Cenozoic when you've had the opposite transition from like the Mid Pleistocene Transition. So you're actually going from the 100,000 year period, that switches off and you get the 40,000 year one. So I don't know if you have an idea of what mechanism that could be.
Yeah, no, I don't know. Don't know much about Cenozoic ice ages. I actually didn't even know there were we knew about ice ages of that frequency back then. Of course, there are kind of these many snowball events and stuff, but yeah, no, I can't comment, but then
okay.
I'd be intrigued to find out more.
Yeah. I mean, the data gets worse and worse the further back you get, so it's difficult. Okay, well, cheers.
Thanks, Will. Thanks for coming again. I think Peter Shearer.
Yes, hi. Thank you. That was a really interesting and informative talk, and I'm intrigued by how the GIA, GIA, when you include that, it can change the period such that even though the eccentricity is very small in terms of the solar function, or the solar differences that you have that change. And this may seem like kind of an odd question, but I'm wondering, in your modeling, if you were to turn off the eccentricity so that that was no longer present, then what would the models do when you include the GIA? Would you stay, at the obliquity period, or would that be damped somehow, but you wouldn't switch to the 100,000 year period?
Yeah, that's a really great question, Pierre, because I think honestly I'd get the same results, and that's not because and I think it's because I think for the longest time in the paleoclimate community, the eccentricity for the feeling was what about eccentricity changes could give us 100,000 years, but it's clear that the field is moving to a point where it's more that it just happens to be eccentric. It's actually more likely that there are sort of interactions, couplings between the precession and the almost that
you're saying it's just a coincidence that it lands on the eccentricity.
Some people have said basically it's really how long it takes to, what's the sort of span of the North American continent in accommodating an ice sheet. And it just so happens these timings all work out in terms of, certainly that's what I read out of Abby Uchi's paper. So this was the paper that first came up with the 100,000 years, that there's just so little in the eccentricity. It's more that like you reach this kind of maximum within, within certain systems exterior to Milankovitch. But in the wording of like the draft I write, I'm very careful in the sense I call the 40,000 years obliquity paced, and I think I forget what I use, but something like eccentricity related. But I think it's a really good point. But my understanding is that the field is sort of moving to a point where it's not. It really is some sort of kind of combination between how the Earth responds, but also more couplings between the 40 and the 20 that could give you 120 versus 80. It's very detailed time series stuff that that goes into these ideas.
Okay, and I guess you don't have a long enough time series to really nail the period, so you could be. I mean, you could see exactly what it is. And,
and it's also quasi-periodic, right? I guess, like, some of them slight, that it's I guess that's nature, but yeah.
Okay, thank you.
Thanks, Peter.
Thank you, Peter. Yuri?
Yes, Harriet, thank you for a nice talk. I was wondering, there are these fairly well-established theories for the links between changes in topography and erosion and the rates of carbon sequestration and release, which obviously have to feed into climate. So I was wondering if this is at all relevant to the post-glacial rebound, or maybe the topography changes of a few hundred meters are just not large enough for this to be significant. I was wondering if you or somebody else thought about this.
Yeah, people have definitely thought about this, whether kind of the, so when, you grow an ice sheet, you actually get the peripheral bulge around the ice sheet, right? And those sorts of changes in topography, can they are they big enough slope changes that erosion changes? So I've definitely not focused on that, but you know, one thing that is worth mentioning is that, you know, they're kind of underpinning this and all the other ideas behind what could have caused the mid-Pleistocene transition is a drawdown in a cooling of climate. And a lot of people have suggested that we really have, it's really hard to constrain that a drawdown of CO2 could cause this. And so exactly what you're saying is that a combination of, are we kind of actually sequestering more CO2 in terms of the erosion and the in terms of, you know, weathering while all of this is happening is a big question. I don't think people know very well, I haven't got some, so a paper I cited here, I'm happy to send it to you afterwards if you're interested, that basically not only was it the regolith removal, you know, as you grow an ice sheet, I mentioned that there's a theory where that ice sheet starts changing its base through eroding the regolith, but what they also model paired with that is the CO2 changes because of that erosion. But again, I think from reading that paper, it's quite an unconstrained problem in terms of how those things all change and what does that mean for CO2 sequestration. But again, it's like all these connections between different systems that seem to be very important.
All right, thank you.
Thank you, Yuri. More questions? I wonder if there are more questions from the audience. If no, let's thank Harriet again. Thank you for the wonderful talk.
No, thank you for staying. And again, I apologize for not being there in person.
I hope we can like invite you in person in the future.
Plenty of great geophysicists to meet one day. All right. Thank you so much.
Thank you so much. Yeah. I'll stop the recording and